In this video we're going to briefly revisit the full telegrapher's equation to examine how lossy transmission lines differ from lossless lines. I've included the full telegrapher's equation on this slide, and I've highlighted a term called the dissipation term. Solving tricky partial differential equations is outside the scope of this class, so you either have to take my word that this term causes dissipation, or read the article I've linked on the course site. The effect of this term is a behavior called attenuation, where energy in a moving wave gets turned into heat in the transmission line's lossy elements. This results in a smaller version of the wave driven into the transmission line, which I've illustrated on the right. The wave at the middle node is a tiny replica of the wave that was driven into the left node. We can be more specific about how small an attenuated wave becomes. We'll do a full derivation of this later, but it turns out that attenuation introduces an exponential scaling factor to the shape of the wave that makes it smaller and smaller as the wave propagates further, and I've shown that down here. The last remaining term in the telegrapher's equation is referred to as the dispersion term. It causes waves to smear out, like the pulse shown in the middle node of the transmission line on the right. So this one here. This happens because waves of different frequencies move at different velocities in a dispersive transmission line. In this example, we know by Fourier that a square pulse is made up of an infinite sum of sine waves, and the dispersed pulse represents fast sine waves running ahead of the slow ones. Dispersion is tough to analyze by hand, so we're going to focus on a few conditions that effectively eliminate dispersion. One condition that eliminates dispersion is when RC is equal to GL, and this is called the Heaviside condition. Another condition that eliminates dispersion is when R is much smaller than j omega L and G is much smaller than j omega C, which is called the low loss condition. We'll take a closer look at these conditions when we drive sine waves onto the transmission line, because the math for sine waves winds up being easier. So in summary, loss causes pulses to shrink exponentially with distance, and that's called attenuation. Loss also causes pulses to spread out, and that's called dispersion. And we can cancel dispersion with certain combinations of transmission line parameters, which we call the Heaviside and low loss conditions, and more on all of this later with sine waves.